Hey, welcome back to Calc 2. In this video lecture, we're going to finish up the material in section 11.2 on infinite series. And in particular, I want to tell you about two kinds of series, geometric series and telescoping series. They're pretty much the only two kinds of series that when we know they converge, we'll be able to find their sums. Typically, we'll be able to say a series converges, but finding its sum exactly is kind of a different question. But for a geometric and telescoping series, we can find their sums. So you're looking at our goals. I want to introduce what a geometric series is, and then derive a test for when they converge. We'll call it the geometric series test, or we'll just add to our acronym list here. It's going to be called the GST. And then I want to tell you what I mean by a telescoping series. And then finally, we'll just discuss some properties of convergent series. Okay, so let's get going. What's a geometric series? Well, it's a series with a special form. What is the form? You start off with some number, A. A is called the first term of the series. And then you take some other number, R, it's called the common ratio. And how you form subsequent terms is you just keep multiplying previous terms by R. So I take my A, I multiply it by R. Then I multiply that by R. So I'd get AR squared. I haven't written it here, but the next one would be AR cubed, and so on. So you've multiplied by R n minus 1 times. You have something like A times R to the n minus 1. And we're going to sum that as n goes from 1 to infinity, right? Because if n is 1, n minus 1 is 0. That's why you get the first term with no R in it. Why is R called the common ratio? Well, if you took any term of the sequence and divided it by the term that's right before it by the rules of exponents, A is canceling here. I've written over there that A is not 0. So for any n, the ratio of two consecutive terms is the same. That's why it's called the common ratio. Okay, so I want to derive a formula for the nth partial sum of a geometric series. So I've got my nth partial sum written here, Sn, and it's A plus AR squared up to the nth term of this sequence. The nth partial sum would end with, when the counter is n, the term is A to the R n minus 1. And then what do? I multiply that sum by R. If you like, this is kind of a little algebraic trick, but if you multiply that sum by R, well, you multiply A by R, you get AR. You multiply AR by R, you get AR squared, and so on. The last term, AR to the n minus 1 times R, would be AR to the n. And then I'm going to subtract. I'm going to subtract the second row, or the first row from the second row. And notice when I do that, there's going to be a lot of cancellation, right? Like this AR is in both rows. It's going to cancel. AR squared, subtracted from itself, it's going to cancel. I haven't written it here, but A times R to the n minus 1 would cancel with the term that's right before A times R to the n. All of those things would cancel. The only survivors after the subtraction would be the very last term in the second row, AR to the n, and the very first term in the first row, A. And if I factor A out of that, and if I factor Sn out of the left-hand side, then I can solve that for Sn. Sn is A times R to the n minus 1 over R minus 1. And typically in books, we'll sort of flip both of those signs and write this as, and there's no reason to do this, but I want the formula to match what's in the book. All right. So if you couple this is kind of cool. We have an expression, a closed form expression for the nth partial sum. So we have a chance of taking its limit. Yeah, I can take the limit of this expression. And the only place in the limit where there's an R, I wish I wouldn't have just highlighted those things, is right there. That's the only place that n appears in the whole expression. So what happens to that as n goes to infinity? Well, we just have to remember, well, what happens to R to the n? What happens to R to the n as n goes to infinity? Well, it depends on the size of R, right? If R is less than 1 in absolute value, then that expression is going to go to 0. And if it's bigger than 1 in absolute value, it's going to blow up. And here in my notation, I should have already kind of written that I can't let R equal 1 But if r is equal to 1, then this series is just a plus a plus a plus a, so it's going to diverge unless a is 0. All right, so if you roll all that together, you get what is called the geometric series test. Here I just clipped it out of your book, so it's in these notes a little nicer than what I would be willing to write it. So the geometric series test says that if you take a geometric series, sorry about that, something on my screen. You take a geometric series, a times r to the n minus 1, so its first term is a, its common ratio is r, then that geometric series is going to converge if r is less than 1 in absolute value. And we even know what it converges to, because if r is less than 1 in absolute value, this r to the n up here is going to go to 0. So we end up getting a in the numerator and 1 minus r in the denominator. So we know its sum. It's the sum of a convergent geometric series. If r is greater than or equal to 1 in absolute value, the series diverges. So this is kind of the nicest test we're going to get, the geometric series test. It not only tells us a perfect condition on when it converges or not, but if it converges, we even get to know the sum. All right, let's try it in a couple of examples. I try to leave the test in view here. So here I've got a geometric series. Maybe you want to pause the video for a second and answer these questions before I write them. But can you see what my a is? If we wrote out some terms, when n is 1, n minus 1 is 0. So this series starts off 7. And then it would be 7 over 3. And then it would be 7 over 9, and so on. Yeah. So what is the a? The a is 7. The r is 1/3, so that's a convergent geometric series, and I can even tell you what it converges to. It converges to 7 over 1 minus 1/3. That's 7 over 2/3, or what is that? That's 7 over 2/3 is 21/2. So this infinite sum, quote unquote, equals 21/2. And you guys know what I mean by that. I mean, if you added more and more terms to that thing, the partial sums would get closer and closer to the number 21 over 2. All right, pretty cool. All right, let's try it again. Got another geometric series. I just tried to disguise it a little bit on you here. I've thrown in some, so it's not so clear what the r is. But if I just use a little bit of rules of exponents, -1 to the n times 2/3 to the n, I can write that as -1 times 2/3 to the n. All right, so there I see my r. Maybe you're a little nervous here that I've started the sum at 0, but notice that my exponent is an n. So if you're ever nervous about what the first term is, don't be, just write it out. When n is 0, this will be 5. And then when n is 1, I would multiply 5 by -2/3, so I'm going to get -10/3. And then I'd multiply by 2/3, a -2/3 again, so I'll get plus, can you help me, 29ths, minus, and so on. So I can see that my first term is 5, and that my common ratio is -2/3. And the geometric series test says as long as that common ratio is less than 1 in absolute value, the series is going to converge. So this series converges. I wish I would have left a little bit more room to work here. I feel like I'm smashing this stuff in. It converges to first term over 1 minus the common ratio. So in this case, that's 5 over 1 plus 2/3. And should I squeeze it in here? That's 5. 1 plus 2/3 is 5/3. So in this case, we end up getting look at that, it's 3. So that series converges to 3. Okay. Sorry about the messiness here. Maybe if I just try to move that down a little bit, it'll look a little better. How about this geometric series? It starts off, n is 1, so it starts off 2. The first term is 2. Then when n is 2, it's 2 squared is 4, times 2 is 8, and so on. So here our a is 2, our r is also 2, which is bigger than 1 in absolute value. So this series diverges by the GST, the geometric series test. Neat. Here, let's do kind of a little example. I guess I have to kind of reveal this as it goes. Sorry, this is going to be, I'll just show you. I don't know why I hide it. So suppose I wanted to write the number alpha, which is 0.17, 0.17, 0.17, repeating as a fraction. Because that decimal pattern repeats, I know it can be written as a fraction. So here's how to kind of think about that. Let me think about, I wish I wouldn't have highlighted those things. Let me surgically get rid of my highlights because now I want to do it again. I'll change the color. What is this first 0.17? Well, that's 17 hundredths, yeah, 17 over 10 squared. And then the next 0.17, that stands for 17 10,000ths. That's 17 over 10 to the fourth, and so on. The next 17 would be 17 over 10 to the sixth, 17 millions, and so on. So that number alpha is just the sum of 17 over 10 squared plus 17 over 10 to the fourth plus 17 over 10 to the sixth. That's a geometric series with first term 17 over 10 squared, and each term is found by multiplying by 100th, by 1 over 10 squared. Yeah. So it's a convergent geometric series. 1 over 100 is less than 1. So this thing converges by the geometric series test. And what does it converge to? First term, 17 over 100, divided by 1 minus the ratio. You can check out the arithmetic there. So that number, 0.17, 0.17, 0.17, that's the same as the fraction 17 over 99. Maybe, I hope in the Zoom meeting for this stuff next week, we'll look at some more applications of geometric series. They have some kind of cool, fun math problems. Okay, so that's the, let me go back up to the top just to check for myself. Sorry about the dizzy scrolling, but we've introduced geometric series. We've got the geometric series test. Now it's time to look at something called telescoping series. Telescoping series. Again, I kind of wrote this out ahead of time, so let me just kind of walk you through, or you can pause if you don't want to listen to me and just walk through yourself. So what have I got? I want to look at the series whose terms are 1 over n times n plus 1. So I'm going to use that integration technique that we talked about, partial fractions. I'm going to take that fraction 1 over n times n plus 1 and try to write it as something over n times something over n plus 1. And I won't take a bunch of time here in the video. You can check out the partial fractions, but this is what I did. I multiplied both sides by the denominator. I'm choosing my strategic values of n. You can do this at a slower pace, but that reveals that b is -1 and a is 1. So I can write my series terms as 1 over n minus 1 over n plus 1. So maybe let me come up here and just rewrite this thing. So this is the sum as n goes from 1 to infinity of 1 over n, take away 1 over n plus 1. So it's in that form that I'm going to start looking at, say, the kth partial sum. So the kth partial sum, when I let k equal 1 in that sum up there, well, I would get 1 over 1 minus 1 over 2. And then when k is 2, I'd get 1 over 2 minus 1 over 3, and so on. The last one, 1 over k minus 1 over k plus 1. And if you look at that thing, again, there's a lot of cancellation going on. This is why people call it telescoping. Except for the first and the last term, everything shows up with opposite signs. I got a minus a half and a plus a half. I got a minus a third and a plus a third. I got a minus a fourth, there'd be a plus a fourth. This 1 over k, the term right before it would have had minus 1 over k. So the only thing that survives after the telescope collapses, if you can imagine that, would be the first term, 1, and the last term, 1 over k plus 1. Cool. So we have an explicit formula for the kth partial sums. This is pretty rare. Most of the time when we have a series, we won't really be able to get this far. For geometric and telescoping series, we can. So I can take the limit. I can, let me write it from the top. This series, the sum as n goes from 1 to infinity of 1 over n times n plus 1, well, by definition, is equal to the limit, I'm going to call it k, because I wrote the partial sums as sk, of 1 minus 1 over k plus 1. And that limit is clearly 1. So we have a convergent series. Yeah. So a telescoping series is one in which in each successive term in the partial sum, something shows up with the opposite sign. So the partial sum collapses, if you like, into just its first term and its last term. That's why it telescopes. Okay? So looking at one more, it's two more examples, and I kind of clipped this one from the book. I'm going to go super fast through it too, so you can pause this thing if you're getting tired, but let me just try to explain what I'm trying to do here. So we looked at a series 1 over n. The sum as n goes from 1 to infinity, 1 over n. That series will come up a lot. It's got a name. It's called the harmonic series. All right. So, and you might recall from the previous lecture that the divergence test failed for the harmonic series because its terms go to 0. And when the terms of a series go to 0, the divergence test has nothing to say. I clipped this example from your book. I'm just going to walk you through it. It proves that the harmonic series diverges. Okay, so the series whose terms are 1 plus a half plus a third plus a fourth, the claim is it diverges. Let's look at this argument. It's not my argument. It's from your book, where the author credits. I can almost remember. It's French. I don't know how to say the name. It's like Orsom or something like that. You can look in your text. Okay, so what are we doing? We're going to look at some strategic partial sums. I'm going to skip S1 and just look at S2. S2 is 1 plus a half, yeah, because the first two terms are 1 plus a half. And then we're going to skip over S3 and look at S4. S4, of course, is 1 plus a half plus a third plus a fourth. But I want you to focus on the third and the fourth. Both of those numbers are bigger than or equal to a quarter. Yeah. So if I replace 1/3 and 1/4 with 1/4 in both instances, then I'm making the sum smaller. Okay, that's kind of the secret of the argument, is that we're going to replace some of those terms. The 2/4 add up to a half. So if you sum all of that up, you get that the second, or the, sorry, S4 has to be strictly bigger than 1 plus 1, or 2. And then likewise, we're going to look at S8. S8 is, of course, the sum of the first 8 terms. So that's what he's got written on that first line. Let me just get your eye to look at it. Sum of the first 8 terms, okay? But then he's going to do some grouping. The 1/3 and the 1/4, he's replacing with a quarter again. These other guys, 1/5, 1/6, 1/7, 1/8, they all get replaced with an eighth, and that would make the sum smaller, because 1/5 is bigger than an eighth, 1/6 is bigger than an eighth, 1/7 is bigger than an eighth. Okay, when you replace terms in a sum with smaller quantities, you make the sum smaller. Okay, now add them up. The arithmetic is so nice here. You've got, can I do one more color? You've got this half. These 2/4 make another half. Those 4/8 make another half. So you get 1 plus a half plus a half plus a half. So we know that that S8 is bigger than 1 plus 3 halves. Okay, I'll skip over the 16. You can look at it. It's the same kind of idea. Same thing for 32. Do this over and over and over again. This is the punchline. The 2nth partial sum is going to be bigger, strictly bigger than 1 plus n over 2. And 1 plus n over 2, as n goes to infinity, goes to infinity. So these partial sums are bounded below by something that's becoming infinite. The author wrote it much nicer here. The partial sums have to go to infinity as n goes to infinity. So the harmonic series must diverge. Okay, so you can ask me about that argument in class or just try to digest it. It's a very clever argument, bounding these partial sums below by something that's going to infinity by strategically picking some of them. Okay, so you can look at this in more detail without all my color in your text on page 713. And then I'm going to end this, what I hope is not too long of a lecture, by just showing you, again, something from your text. I was going to tell you the page numbers when I do stuff like this, and I didn't. Let me tell you, it's page 714. Sorry about that. Where you'll find this lovely table, and it's the usual properties. The usual properties, when you have two series and they're convergent, you multiply it by a constant number, that'll still converge. You add the series together, you subtract one series from another, those still converge, and you get these usual kind of formulas. Yeah, this just looks like the distributive law. You can pull a constant out of a convergent series. If the series AN and BN both converge, then their sum would converge to their sum. Their difference would converge to their difference. Products and quotients are a little bit trickier, so we we won't include them in these properties. So let's just end with one example. Here I've written a series, yeah, sum from 0 to infinity. It has a difference of two terms, so it kind of looks like property 3 there. So if I just think out them one at a time, the sum from 0 to infinity of 1 over 3 to the n, that's a convergent geometric series. Common ratio is 1/3. The sum of 1 over 5 to the n, that's also a convergent geometric series, yeah? So this property 3 up there says that this series converges. And what it must converge to is the sum. Sorry, I'm being a little lazy and not writing my indices. The difference, rather, of those two series. And well, let's use the geometric series test one last time together. This one's common ratio is 1/3. Its first term is 1. So that first series converges to 1 over 1 minus a third. The second one converges to 1 over 1 minus a fifth. Yeah. So that's 1 over 2/3. That's 3/2. This is 1 over 4/5. That's 5/4. Well, and I guess we could say that that's 6/4 minus 5/4. So that's a quarter. So this is a convergent geometric series, or sorry, excuse me, it's not geometric, but it's a convergent series, and it converges to a quarter. Okay, thanks for listening, and I'll see you in a Zoom class.